Okay, this is part 2 of our chapter 15 material. I think we need to focus. There we go, much better. All right, so in part 1 of statistical process control, I introduced you, I hope, to what it is, why it's used, how it's used, what the charts look like. And now what I wanted to do was go through an example. It's a text example. It's a good one, to show you how the computations would be made. So for example, suppose that in the example, we have a sample of 5 items. Now, they don't really go into what the measurements were here, but in this case, my sample size is 5. In the previous lecture, I told you that there are 2 N's in statistical process control. There's the sample size, which is 5, and then there's the number of samples, which is N. That's 20. So there are 20 samples of size 5 that were taken here. Now, for each one of these samples of 5, the sample mean is computed and the range is computed. So let's just go over here. This 31.6, where did that come from? That is the average of 33 plus 29 plus 31 plus 32 plus 33, all divided by 5. And where did this 4 come from? Well, that's the largest value here in the sample. And you can see that the largest, there's a tie there between X1 and X5, but that was 33. So I take the largest minus the smallest, which was 29. So that's where we get the 4. And then that will be done for all of the 20 samples all the way down here. And then what we're going to need is we're going to need to know, it's hard to see this, this is X double bar. That's something that we call the grand mean. And here is R bar, and that is just the average of the range. Now, where did this 33.32 come from? There's a number of different ways you can do it. You could have summed up, double summed up here, all of these values, there's 100 of them, and you would have gotten 33.32. The easier way to do it, and the faster way, is just to see that it's the average of all of the X bars. So this 33.32, that's that 31.6, I'm not going to write all 20 here, plus 33.4 plus, and then the last term would be that 33.8, and then we would divide that by 20, and you'll get 33.32. R bar is just going to be the average of all the ranges. So this 5.8, that is the 4 plus 6 plus, and then the 20th one here would be a 6, and that would all be divided by 20 as well. Now we need those values because what we want to do is create our X bar. That's what this chart is here. This is my X bar chart. This is my R chart. This X-axis, this is the sample number here. And then these are the values that we're going to be plotting. Now, what we said in part 1 of these lectures is that we need to compute an upper control limit, a lower control limit, and a center line, which is also known as X double bar. So sometimes we call that CL, the center line. Same thing for the R. R bar is also called the center line. And we're going to use these formulas to get that. So the upper control limit for my X bar chart is going to be X double bar, the center line, plus that constant A2, which we said we could get in the textbook. And I said I would provide it for you on the exam. And so in the previous lecture, I showed you that here's a list of the constants for X bar and R charts. And so because we're using a sample of size 5, then we're going to need A2 is going to be 0.577. D3 is going to be 0, and D4 is going to be 2.114. So the A2 is used in the X bar chart, and then the D3 and the D4 are used in the R chart. So let's write down those constants because we're going to be needing them. So A2, which I just got from that slide here, A2 will be 0.577. D3, as I said, was 0, and then D4 was 2.114. And then we're just going to use these formulas. So the book already did it, but this upper control limit, this 36.67, I'll tell you where that came from. That's going to be X double bar plus A2 times R bar. So all of these values have been provided for you. So here is R bar, X double bar, A2, D3, D4. That's what you need to compute these limits. So I'm just gonna, rather than clutter this up even more, I'll just show you where the formulas are. Then we have this center line, which was X double bar, which is down here. And then my lower control limit, that's gonna be X double bar, the grand mean, minus A2 times R bar. And if you punch those in, you're gonna get exactly 36.67 and 29.97. For the R chart, the way we get the upper control limit, it's just a little bit different. The upper control limit ends up being this constant D4 times R bar right here. And then the lower control limit, that will be D3 times R bar. So an interesting thing about the lower control limit of the R chart is that whenever my sample size is bigger than 6, that D3 will be a 0. And a little piece of information is that on the final exam, I generally will not put a sample size bigger than 6. So tuck that away for what it's worth. Oh, shoot, you can't see this. Here. There we go. Oh my gosh. I can't make this high enough. Goodness. There we go. Okay. So I see that I didn't quite get that in the view here. Okay. So now, how is this chart used? Well, what we're going to do is we're going to go through and we're going to see which points are considered to be out of control. And it doesn't matter if you have a point or a sample out of control on either chart, the whole sample is considered to be out of control. So you don't have to have both of the X bar and the R values be out of control for it to be out of control. You have to just have one of them. So the easiest way to spot the out of control, and I was looking for another highlighter here, but I don't really see it. So I'm just going to circle them in red. If I scan down here, this X bar, these X bars, I'm looking for any that are bigger than 36.67. And you're going to see that the first one is going to be this sample number 6 is bigger than 36.67. Sample number 8 is bigger than 36.67. And by the way, I'm going to circle them on here. And the authors chose to put a 1 there. I kind of wish they had just put a little star, but that's okay. This and that. Then there was another one that's out of control here. Sample 11 is below the lower. That's 29.97. This one is 29.8. So that's this point here. And finally, sample number 19 is also out on the low side on the X bar chart. But we're not done. We have to look at the R chart as well. So now we're going to look at, is there any point above 12.27? And we can see pretty quickly that there is, and that's going to be sample number 9. And that's the only one that's out of control on the R chart. So if we were a data analyst or an engineer on this process, what we would say is that samples, and here they are, 6, 8, 9, 11, 6, 8, 9, 11, 19, and I got that one. 6, 8, 9, 11, and 18. That's it. 1, 2, 3, 4, 5. Yep, sorry. I was going to try to differentiate between charts. Are showing out of control, are showing as out of control. So you don't have to have both X, because notice it's kind of interesting. Like, look at sample 9. It's out on the R chart, but not out on the X bar chart. But that doesn't matter. It's telling us that this one measures variability. This one measures the mean. So for these points, the point right here that I'm pointing to, those are showing that my mean is showing unexpected variation. And This one is telling me that my standard deviation or my variance is showing unexpected deviation as well. So then what would you do with this chart? Well, what you typically, well, I'm going to get to that in just a second. Hang on here. Hang on. So each time we're plotting something on an X bar chart, we are actually doing kind of a mini hypothesis test. So you can kind of think, if you were to say, turn this around, like maybe this, you can kind of think of it as these bounds here, the upper control limit and the lower control limit. These are kind of like, remember what we did? We did acceptance region and rejection region when we did hypothesis test. That's kind of like that. So whenever we had a test statistic, remember, that was between two values for a two-sided test, we said that it was we would fail to reject H naught, and whenever we had a value that was outside those values, we would say that we reject H naught. Well, it's kind of the same thing. Each one of these points is a little hypothesis test. So right here, what we see is a process, this is another process, that appears to be in control. So for this particular example, we have an average ring diameter, and what we can say here, right here, I'm going to do a hypothesis test. There we go. And this would be sort of like each point would be testing, is the mean equal to 74? Because that was the center line. I mean, that's what this is right here, center line or X double bar. And out of control is like saying we're going to reject H naught at any particular point in time. So how do we, what do we do with the chart once we've got it? So we can see we have 5 points out of control here. What would we do if we saw that situation? Well, what you would do, and I've got an algorithm for it coming up here. What you would do, you're supposed to investigate all of these things. So what you want to do is investigate to determine the cause, because these points are showing unexpected variation. So you would want to go back and you would want to look at the samples that comprise sample number 6. So you might want to, find the serial numbers of these guys and maybe the serial number of these guys, but not just that. You also want to look for maybe some environmental conditions. Maybe we had a new operator doing it, maybe something. But what you're supposed to do is investigate to determine the cause. Once you've determined the cause, and sometimes you can't, but you're supposed to, then what you do is you remove all of these samples, every one of them that showed out of control. Once you figure out what was wrong, you remove them from the data set. So we pull all of those out, and then we'd recompute the upper, the lower, and the center line for both charts and do it again. And we might have points out of control then too. So it's an iterative procedure. And that's what this next slide is talking about here. How to create and revise a control chart. And this is how you would do that. Another pen here. Let me see here. All right. So first you would compute the sample mean, and we say xi bar for all samples, and I is going to go from 1 up to capital N, that's the number of samples. Compute the range Ri for all samples, I equals 1 up to N. And then find the appropriate values according to the sample size, and that was from this chart right here. You find these here, make sure you know what the sample size is. Then you're going to compute the upper and lower control limits for each R and X bar I. And then you're going to determine which sample indices are, and again, out of control. Then you investigate, determine the cause, figure out the corrective action. Then you remove those samples, as I said, from the data. Do not remove, this is so important, until the assignable cause is found. Sometimes you have to, but I didn't say that. And then you just repeat steps 1 through 9 until the process is actually in control. And then you watch it. And remember, sometimes a chart can look, I said this in the first lecture, sometimes a chart can have points that are all between these two limits, but sometimes they can have things that are called cycles or runs. And in other words, sometimes you might have, what if we kept going here and then we had a bunch of points that were all down here, like a lot of them in a row. That might indicate an out of control condition, but it doesn't mean, it may not show, in terms of being outside of the limit. So sometimes you have to use your best judgment if you're the process engineer or the analyst for that process. Okie dokie, that ends this lecture. Have a great day or evening.